Mr. Tom Mulder. Thank you, Tom.
Good afternoon, everyone, and thank you for attending today's performance, if you will. I'm here to describe the CST-100 Starliner spacecraft. It is the next generation of human spacecraft to get crew to and from the International Space Station. Before I get started, I'd like to acknowledge 4 people, starting with my wife, Ann, sitting over here on my right, and then Mike and Doreen Frietta, both from Houston. Mike is basically the wizard behind the curtain for developing the algorithms and equations and all the hard stuff in the software that allows us to fly our spacecraft during rendezvous and docking with the space station. The 4th person, I listened to Vinny talk this morning. I was very interested in his father, who inspired him growing up. The same was true in the case of my father. He made sure that the 3 children sat in front of the black and white television to watch the moonwalkers back in the late 60s, early 70s. Later, he bought me a telescope in junior high, and then again in high school, subscription to Sky and Telescope magazine. And so eventually, he took me to a point 1 hour north of Winnipeg, Canada, for the 1979 solar eclipse. Quite a drive back in those days. So he passed away 3 months ago, but I want to remember him here as well. Okay, the CST-100, before I dive into the actual spacecraft itself and how it flies, let me give you a little bit of background. Back during the George W. Bush years as president, the president established a policy working with NASA called Constellation. And Constellation said, instead of focusing on low Earth orbit with space shuttle missions, we would instead focus on getting crew to and from the moon and eventually to Mars. Once President Obama became president, he stuck to most of the pieces of that equation, but he added a few more of his own. Instead of having a single spacecraft called Orion perform all manned missions, not only to deep space, but also to the International Space Station, the new president said, let's let NASA focus with the Orion capsule and the new Space Launch System on getting just to the moon and to Mars, and let's let some commercial companies take care of getting crew to and from the International Space Station. And so he established the Commercial Crew Program, and this all started really way back in 2009. And so when we got wind of that in Boeing, and other companies did as well, we established a small team in Houston and in Huntington Beach. I was a member of that team, heading up the mission design and mission operations portion of it to basically define the fundamentals of when we launch, how we dock with the space station, how do we deorbit, and where are we going to land afterwards for Boeing's entry into this competition. That led eventually in 2014 to a final contract that Boeing and SpaceX also won. And so between these 2 companies, we are competing today to eventually be the suppliers of the spacecraft, both of which are capsules, just like the Orion capsule, to get crew to and from the space station. And so we've been working on this for a long time, and we plan on launching later this year. I believe SpaceX intends to do the same. And so this presentation will describe the spacecraft that Boeing has been developing and will be launching this year, as well as focus on the mission operations and the rendezvous and docking and other aspects of the mission itself. Okay, so what you see here is a complete cycle from a concept of operations standpoint, starting in basically the lower right corner where we assemble the spacecraft itself, which really consists of 2 parts. There's a crew module, which gets reused flight after flight, can be used up to 10 times, and then there's a service module that gets built and replaced after every mission. That's being developed, the hardware in concert with all the software. There's flight software that commands the spacecraft, there's ground software, and then there's mission operations that ties all this together. So this leads to pre-launch processing and preparing the vehicle for launch, and then that eventually leads to the pad operations. Boeing selected United Launch Alliance, or ULA, to launch our spacecraft. So unlike SpaceX, who's building a complete rocket and capsule combined, we're focusing on the capsule itself, and then we've chosen the Atlas V rocket to be the means to get us into suborbit, and then eventually from there we go and dock on our own. So all this takes place at Pad 41 in Florida. That's where all the launches will take place. And then after launch, that capsule drops us off into a suborbit. It's not a full orbit. We did a trade study on that and decided we could get more mass to orbit by dropping us into a suborbit, meaning that if we don't do anything after that, we re-enter the atmosphere, of which we do safely, by the way, if it comes to that. But after we separate from the launch vehicle, and that's about 15 minutes after launch, then we're off and running, and we're doing rendezvous and docking to the space station. The period of time that the operational spacecraft will be docked to the space station is approximately 6 months. That's not based on our doing, that's based on NASA's standard schedule. They typically rotate the space station astronauts every 6 months. As you know, there was an exception made where an astronaut stayed up there for an entire year, and if that's the case, well, that's fine. But requirements-wise, NASA said, stay up there for 6 months, up to 7 months if necessary. So the vehicle is really designed to stay docked to the space station for up to 7 months. After that, it separates from the space station and performs a deorbit burn, and then it does a land landing at one of 5 landing sites. And I'll get into more detail on these operations and exactly where those landing sites are in just a minute. As I mentioned, the capsule itself can be flown as many as 10 times. The service module, on the other hand, is separated and burns up, and we build a new one of those every flight. So it's very, very similar to the old Apollo system, but it's much bigger. Instead of holding a crew of 3, we can hold a crew of as many as 7 people if we really pack them in there, or a combination of fewer than 7 plus cargo to go with it. So a few things. The CST-100 Starliner spacecraft, as I mentioned, is both a CM and an SM, crew module and service module. That's a major element that's manufactured in Florida in one of the orbiter processing facilities. Back when the orbiter flew, there were 3 processing facilities. After the shuttle landed, it would be dragged into an OPF, be refurbished, and then taken on to the vertical assembly building and launched again. Since many of the shuttle facilities were no longer needed after that, Boeing stepped in and said, well, we're interested in one of those 3 orbiter processing facilities in Florida. And so we're basically leasing that facility right now at the Kennedy Space Center. The United Launch Alliance Atlas V rocket has now flown 77 times. All 77 missions are considered successful, and it has the lift capacity needed for our heavy capsule, and therefore we chose ULA and the Atlas V as our means of getting to and from orbit, not from orbit, but to orbit. Mission operations. This is a key area that we decided to basically do mission operations with NASA directly rather than performing the operations ourselves. What does that mean? We basically have a contract back to NASA, Johnson Space Center, the same folks that used to operate the Space Shuttle itself. They did the planning, they did the training, they do the flying, and we are actually using the very same people and many of the same documentation, same techniques, same software that they did back on the shuttle program. So it's a proven group of folks. We know we can trust them, and we've had a very good working relationship with them. In fact, our mission control center itself during the flight is actually located in Houston in the same building and possibly the same room that the shuttle mission control center itself was held in. So there's a lot of similarities and experience carried over from previous programs to the CST-100 Starliner program. And then last but not least, the ground processing operations. We have an entire Boeing ground team that processes the vehicle at the Cape and then takes care of the vehicle after it lands, preps it for delivery back to Florida, and then gets it ready for the next flight. So, United Launch Alliance, as I said, has had 77 successful missions with the Atlas V. They've never launched an Atlas V with humans on board. This is the first time such a cargo has been done. They've spent many years looking into doing this before this program ever came along, so they got a head start on it. But there are a number of features, and you'll see those in blue on here, that in fact are new compared to their standard cargo launch vehicle. In particular, the most notable one is the crew access tower. And the tower is, of course, the place where the crew and ground personnel take an elevator to the top, and then they climb into the capsule and have direct access to the capsule, as well as access outside the capsule in the event that they have to do an emergency escape from the rocket. And so numerous provisions have been put in place at Space Launch Complex 41 in Florida to accommodate crew and safety and everything associated with that. So the capsule itself, as I stated, there's a CM, that's the triangular capsule at the top end, and at the base of that is the service module. And so the crew module obviously is where all the crew sits and performs all their activities. There's also cargo in there mixed in with the crew. And then a lot of the smarts and the expensive pieces that we want to reuse from flight to flight are also in the crew module. That includes a set of computers, integrated processing units, the displays, controls, etc., needed to basically the brains to control the vehicle itself, meaning control of both the CM and then also the SM. The service module, which gets disposed of every flight, has the thrusters on board. It's got the big propellant tanks, and it's basically the tug on the vehicle that when we're on orbit, flies it during rendezvous and docking, separates from the space station, does the deorbit burn, and then after the deorbit burn, it's gone, and it's just the crew module that performs entry, descent, and landing. If you look in that lower left-hand picture, you'll see a crew of 5. This is one configuration for flying crew to and from low Earth orbit. As I mentioned, we can fly, if necessary, if desired, up to a crew of 7. And so if there's a crew of 7, there's an additional crew person down in the lower left bay and in the lower right bay as well, in place of cargo. So that's a pretty tight fit, but it does work. The requirement from NASA is actually not to fly 7 or fly 5, but really to fly a crew of 4. So what they would like us to do, and SpaceX with their Dragon as well, is to send a crew of 4 up every 6 months. The vehicle, once it gets docked, stays docked. That becomes the crew's lifeboat. So the same capsule that got them there brings them back home. So that way, if something happens on station, if there's an emergency, if there's a meteoroid hit or something that renders the space station in trouble, if you will, we have the capsule there, and we have all the software and procedures in place that allow the crew to escape the International Space Station, get on board, and come home. So typical crew of 4, but we can accommodate more than 4. And in fact, if we have other customers beyond the space station, then we can accommodate those as well. But it's really designed as a low Earth orbit to and from. When I say low Earth orbit, that means in the neighborhood of 200 to 250 miles above Earth. Unlike Orion, as I stated earlier, which is really meant to go to the moon and to Mars. So we've been, as you can imagine, extremely busy doing development. They're really going back to 2009, but it's really picked up the pace in the past few years. There's considerable wind tunnel testing that's gone on. The reason being, our capsule is not positioned under a fairing on the Atlas V, but instead is out there in the wind. And so going uphill for those first 12 minutes, we need to make sure that aerodynamically, supersonic speeds, that the vehicle is stable and the rocket can maintain the proper orientation and meet the performance requirements we need at main engine cutoff. The way that we land is with a set of airbags. There's actually 6 airbags that are deployed to soften the blow, if you will, when we land on Earth. This is different from the Soyuz rocket that the Russians fly. The way that they break themselves at the last second is literally by firing a set of thrusters to make sure that they land softly. We considered that as an option, and we thought it was more passively safe to just go ahead and deploy airbags when we're floating under the parachutes, and then cushion the blow that way. We also have a seventh airbag that allows us to splash down in the ocean if necessary. While we're designed to land on land, the vehicle is also designed to land on water. Hopefully that will never happen. It's not our desire. The salt water is actually quite harmful to the capsule itself. But if we have to, in order to get the crew home, if there's an emergency, we get struck by a meteoroid, for example, and need to come home quickly and can't wait until our ground track takes us over a landing site, then we have the ability to take it down over water. You'll see Sunny Williams there in the blue suit. She is one of several astronauts that have been spending a lot of time testing out our displays and controls, helping us develop the procedures to make sure that the vehicle meets their requirements, the Astronaut Office requirements. Another facility we have, and by the way, Sunny and company, they work in Houston. That's where all the astronauts live today, and in fact, that's where all the training along with mission control will take place during the mission. That next picture to the right of Sunny is a test of one of our service module rocket engines being test fired at White Sands test facility, and that's located at White Sands Missile Range in New Mexico. And then in the lower right, that's a test of a drop test with the airbags, demonstrating what kind of loads are applied to the vehicle and to the crew, and that's actually taking place at Langley. So we've got tests going on at various locations. I should have mentioned in the lower left-hand corner, that's a structural test that's going on right now in Huntington Beach with a structural test article. So really coast to coast, we have considerable testing going on this year in preparation for launch later this year. So what's in production today? Well, it all starts with a structural test article of both the crew module and the service module. This vehicle will never fly. It's a common article that's built in the space business and in the aircraft business. And so this is a predecessor to the eventual operational vehicles themselves. So we've delivered this structural test article to our Huntington Beach location, and they have been for several weeks now been basically testing the heck out of it, stress testing, drop testing, really pushing it to its limits to ensure that the capsule and the service module can survive the rigors of ascent and landing, and as well as the vacuum of space in between. The service module has been going through a series of hot fire tests. Hot fire means they light up the engines and make sure that all the engines work properly, the ramp off, the tail off of the engines, the performance, the thrust, everything works properly within the propulsion system itself. Then there's another vehicle called the pad abort test vehicle. And so there's going to be a pad abort test scheduled for this summer at White Sands Missile Range. And the pad abort vehicle will never fly in orbit. This is called our spacecraft number 1, but it's basically launched into relatively high altitude, not high like orbit, but high enough altitude, and then comes down and lands, and we demonstrate that the vehicle can safely abort off the launch pad itself. And so basically we've got the whole range of ascent aborts covered, starting from before we ever lift off, if there's a problem with the launch vehicle, that we can pop off the top, push ourselves out over the Atlantic Ocean, and then set it down. And so we cover the entire range from pre-launch all the way until we've actually separated from the launch vehicle itself. So there's a system on the launch vehicle called the Emergency Detection System that ULA has developed that if it detects a problem with the launch vehicle, it notifies our capsule, and then we immediately jettison very quickly off the launch vehicle and then parachute down into the water over the Atlantic Ocean. So that's another major difference between us and launching just a piece of cargo on an Atlas launch vehicle. The Orbital Flight Test Vehicle is in production today, and this will be the first one that actually flies into orbit. And so we're planning on an orbital flight test later this year, specifically in the third quarter of 2018. And the orbital flight test, I'll get into some of this in detail, but the orbital flight test consists of a complete launch, complete rendezvous and docking with the International Space Station, staying docked for several days, and then undocking and coming home, and then landing at one of our 5 landing sites. Unlike the flights that follow, the orbital flight test will have no crew on board. This is the first time we will have gone through all of this. We have all our primary objectives laid out, and we don't want to take the risk if something were to go wrong on the first time we fly it. And so the vehicle basically flies itself. There's no pilot on board that's needed to grab the stick and point it and dock to the space station. We have sensors on board. We have all the proper software on board that allows us to autonomously go from liftoff all the way to docking, thanks in part to Mike Frietta and the algorithms that he's been developing, as well as undock from space station and then find itself a landing site, do a deorbit burn, and then take itself all the way to the landing site. And then last but not least is the crew flight test vehicle, and this is the first time we'll actually fly crew on the space station. I'm sorry, on our capsule to the space station. And so the plan in our contract that we signed with NASA is that we would have a single Boeing test pilot on board along with a NASA astronaut on board. We'd fly, we'd dock, we stayed docked for up to maybe a couple of weeks or so, and then we'd come home. And basically, by the end of this, we will have certified the vehicle for both uncrewed and for crewed flights, and then we can turn it over for operational missions for NASA. Boeing recently signed a contract amendment, maybe a month or two ago, I don't remember the exact date, but in that contract amendment, it gives NASA the option to fly not 2, but a total of 3 crew people on the capsule on the crewed flight test. What that means is there'd be a Boeing flight engineer, and then there'd be not 1 but 2 astronauts on board if NASA wants to exercise that. A second part of this new amendment is that NASA can load up the vehicle with more cargo if desired, and basically make more use out of this mission rather than just a pure test mission, but make it operational as well and get some better good out of it. And then the third part of it is we've offered NASA the option to keep that vehicle docked to the space station for up to 6 months. So now it really becomes an operational mission with a Boeing engineer and 2 NASA astronauts doing real work, scientific, medical, and other, during that 6 months on board station. So basically stretching out the capability from just a test flight to more of an operational flight. It'll still be a test flight because there's still test objectives that need to be met, but we'll get more good out of it that way. So we're basically leaving that up to NASA to decide how or what they want to do with those options. I'm not here to tell you exactly what their plan is, but you'll be learning more about that in the coming weeks. seen in that video the astronauts testing out the escape lines from the top of the crew access tower. That would be a fun ride all the way down, but that's also something different that ULA normally doesn't do that with cargo. They just let it go. So, okay, so let's go into some detail on the operations here. We launch out of Space Launch Complex 41 in Florida. That's the launch pad immediately south of 39A and 39B where the shuttle used to launch. The launch itself takes about 12 minutes in order to reach what I call a suborbit. And then we separate from the launch vehicle and we're off and running. It's a common misconception that in a rendezvous mission, you launch the vehicle, you get on orbit, you wait a period of time, and you say, okay, now let's go rendezvous with the target vehicle. In reality, we start rendezvous immediately after we separate from the launch vehicle, and we optimize the orbits, both the altitude and the orbital plane of our spacecraft to match up with that of the space station. And so we kick off and we're off and running, fully autonomous mode. Everything is calculated on board the spacecraft in order to make this work all the way up to the space station. So that's the first burn. Here's the second burn, which puts us into a phasing pattern. There's nothing new on our spacecraft here. This is orbital mechanics. This is just straight physics. But if you want to go catch up with another spacecraft in orbit, then you put yourself into a lower orbit, and then you wait it out until you get close to it before you go on in and dock to it. The period of time during this phasing period can be anywhere from an hour or so up to many hours. It all depends on where the space station was in orbit when we launched our spacecraft. And so if the station is in the optimal location, we can get from liftoff to docking in only 6 hours, which means that the onboard crew doesn't need to go to sleep. They wake up in the morning and they go to bed on the space station itself after docking. If in fact the station is further downrange, well, then we're talking a day or two until we can get there, meaning the crew goes to sleep in our capsule, they wake up, then they go to sleep a little bit later, they wake up, and then they can dock. This gives us the chance to launch on any day, any phase angle, however NASA chooses to fly. Whether or not NASA will choose to have us fly with that worst case phase angle where it takes that long to get docked is entirely up to them. They're the customer. But the capability exists for us to fly that way. And then we execute another burn that takes us up closer to the space station, another maneuver and another maneuver, and ultimately it's a total of 6 burns that take place during the course of rendezvous. And when I say rendezvous, I mean not all the way to docking, but getting close to the space station, close being within a few hundred meters or so. After that, we execute a series of burns during what we call proximity operations that takes us up to an approach corridor, and then we approach using sensors on board our spacecraft all the way into docking. If during this time something were to go wrong with our autonomous system, we do in fact have all the capability necessary, switches, controls, software, displays, even a window, for the pilot on board to take control of the spacecraft and safely get it home and get it landed. As part of that, we can also take it in and dock on its own if it comes to that. We don't expect that to happen, but it's always good to have backup systems, especially in this new age of fully autonomous systems with cars and aircraft and drones and so on, so you might be able to relate to that. This is what a typical ground track looks like. It's basically a sine wave. So we launch out of Florida, and we have main engine cutoff over the North Atlantic. As I mentioned, that's about 12 minutes after liftoff. We do have abort zones that going uphill the entire way if something goes wrong, various abort modes, and the last one being that we actually limp into orbit itself, from which we can come home. And depending on where the space station is in its orbit, this can take, as I said, 6 hours, which is about 4 revolutions, or many, many more hours if the station takes a long time to catch up with it. Here's a timeline for a Flight Day 1 docking. It's called Flight Day 1 because the crew doesn't go to sleep. They actually dock on the same day that they wake up. And so, if you look closely, you'll see we got a pre-launch period, and then what you see in MET, that's mission elapsed time in number of hours, and this can be done in as little as 6 hours if the space station is in the right place. Basically, after liftoff, we've got our post-insertion when we get into orbit itself, and then we got our long phasing period, again, doing the major catch-up. That's then followed by maneuvers to get up, height adjust, near-field rendezvous, terminal phase rendezvous. We then do a fly around to the appropriate port on space station and do the initial approach, final approach, and then we're docked to the space station itself. The space station actually has 2 docking ports on it. There's one on the forward end of what's called Node 2 on the very front of the space station. And then there's a second one which eventually will be on the Zenith port, Zenith being the upper port of that same node. I say eventually because there's a docking adapter that NASA still plans on launching later this year that will be put on the Zenith port, which will allow both the Starliner and the Dragon crewed vehicle to dock to once that's attached there. And that way there's redundancy on station to be able to go to one port or the other port, or if we're docked to one and they want to go to the other one, NASA can mix and match as desired between that forward and that Zenith port. For a Flight Day 2 docking, as I mentioned, there is in fact crew sleep period included. This is during the far field rendezvous, and there's really not much for the crew to do other than take pictures and look out the window and enjoy the view. Again, the spacecraft is holding its own orientation during this time, charging the batteries. We have solar panels on the back end of the service module, and there is communications with the ground during this time. The undocking to landing timeline looks like this. Typically, we can get from undocking to landing in between 2 and 5 hours. It's actually very rapid. We try to compress that timeline as much as we could in order to make sure that whatever forecast the weather forecasters come up with when we're docked at the landing site will still hold true. If we undock and we sit around for 2 days like the Space Shuttle used to do, well then all bets are off as to whether we're going to have good weather or not at the landing site. So we prefer to get off, get away from space station, and get home as quickly as we can. And so you see here in the timeline, there's a corridor separation period when we're going outbound from either the Node 2 forward or the Node 2 Zenith docking port. Then there's a fly around, and this fly around can include inspection of the space station itself. One feature the shuttle had after it undocked was the ability to manually pilot the vehicle as it went around the space station, take pictures of it, get views that they can't get from the ground or from cameras mounted to the station itself. So these are unique views, especially if there's a problem with a solar panel or they think something isn't working right. These pictures can be very valuable. So NASA put in place a requirement that called for being able to do an inspection fly around after we undock. So after we undock, we literally fly all the way around the space station before we come home and take lots and lots of pictures during that time. That's followed by a height adjust period of time. We go co-elliptic out in front of station, and then our onboard software goes off, finds us a landing site, executes the deorbit burn, and we're homeward bound. And then post-landing takes place, obviously, to get the crew and cargo out at one of our 5 landing sites. After we execute the deorbit burn, this is the means by which we separate the crew module from the service module. We do the deorbit burn with both modules. We need the propellant, we need the engines on the service module. But after that deorbit burn, our altitude is rapidly descending, and we don't need that service module anymore. We just want to make sure we can survive entry in the crew module itself. And so there are basically 5 steps to this. Number 2 is yaw to a disposal orientation. And this is to make sure when we separate the 2 spacecraft that the service module doesn't come back and recontact with us. So we actually go to a partially out-of-plane attitude, which Apollo did as well. There's a lot that we've learned from Apollo that we've applied, and this is an example of it. We go to this yaw disposal orientation, and then the service module itself, not the crew module, but the service module fires thrusters that separate it away from the crew module while spinning the service module up to maintain a stable attitude, something else that we stole from the Apollo era. After that happens, the crew module is off on its own, again flying on its own, or the crew can take control if necessary to put it in the proper orientation for entry. And while this service module is burning, it just keeps right on burning, and that does two things. One, it gives us good separation from the crew module, but the second reason why it continues to burn is we want to dispose of it not over populated land. In a few charts I'll show you where our 5 landing sites are, but they're all in the western half of the United States. And so we want that service module not to land in the western half of the United States, but instead in the Pacific Ocean, uprange of the landing site. So to do that, instead of coming down like this, we want the service module to come down like that. We'll go to the landing site with the crew module. Service module comes down long ways uprange of that where it's safe and out in the water. This is a typical trajectory coming into one of our landing sites. This is at White Sands Missile Range. White Sands is north of El Paso in the southeastern part of New Mexico. What you see in white here is a typical trajectory coming in as it's burning off energy is what we call it. We actually intentionally underburn a little bit and then burn off energy in order to hit the landing site. That was also done on the shuttle program. That's a typical way of coming in. But we roll left, we roll right, and the orientation of the spacecraft coming in is not nose forward, and it's not even heads up. It's actually the back side of the capsule into the wind, and with this ablative heat shield on the base end that burns off on the way in. It gets extremely hot but keeps the inside cool. As I mentioned, the crew is not face up, they're face down. The crew can actually see the Earth's horizon out the window, and that aids them in the event that they have to do this manually. And then what you see in green and red there, those are typical cross-range limits depending on where the mass properties of the vehicle are located, where the center of gravity is on the spacecraft. We don't want the center of gravity to be right on the center line of the spacecraft. If it is, then we don't have any cross-range control of the spacecraft. We actually want it down below the center line. And so we intentionally design the spacecraft. We put the denser components on one side of it, propellant down on that side of it in order to offset that center of gravity off the center line, which again gives us the chance to steer left, steer right, and give us more of a cross range coming into the landing site. We don't have wings on our spacecraft like Shuttle did, and therefore we don't have nearly the cross range capability that the Space Shuttle had like an airplane does. So it's very important for us. We've done numerous studies to make sure we keep that center of gravity as low on the spacecraft as we can coming in. And so that basically gives us a cross range somewhere between that green line and the red line. This is kind of a 3D view coming out over the ocean to a different landing site. This is Edwards Air Force Base, a couple of hours northeast of Los Angeles. And as you can see, we come whizzing over Los Angeles itself and over a set of mountains before we come out over the dry lake bed, Rogers Dry Lake Bed at Edwards Air Force Base. During this time, we're basically wiggling, turning, if you will, the trajectory on the way down to burn off energy and to hit the target that the onboard guidance software is aiming for. Because on this flight, because we fly over a populated area if we're going to Edwards, we decided on the first orbital mission, the OFT mission, that we would roll out going to Edwards. And so instead of 5 landing sites, we have a total of 4 landing sites available to us on the first mission. After we've demonstrated that, yes, we do meet all the requirements, we do in fact hit a small circle down on the ground, then we can add Edwards to the list, starting with the crewed flight test that follows. So, since it's a capsule, unlike a shuttle, there's entry, there's descent, and there's landing. Entry is the period starting at about 400,000 feet altitude, when the density of the air becomes thick enough in order to actually have an effect on the spacecraft as it flies. And we use that density to slow us down and steer the vehicle during entry. Once we get down lower, we deploy a pair of parachutes called the drogues, and those are done at about 30,000 feet, give or take, a little bit below 30,000 feet. And those parachutes pull off what's called the forward heat shield. Forward heat shield is a ring toward the nose of the spacecraft that protects the electronics underneath it during the high heating periods, but they're not needed once we get this low. And so we do a combination, deploy the drogues, which slows down the vehicle, and we pull off this forward heat shield, which is no longer needed once we get down low. Once we get down even lower, instead of those 2 smaller parachutes slowing us down, now it's time when we need the much bigger parachutes. And so we have a total of 3 larger main parachutes that are deployed, which slow the vehicle down considerably, similar to what you've seen on Apollo, where you got your 3 big parachutes coming out, except we're a little bit bigger, a little bit heavier than the Apollo capsule was. And so these mains come out, they slow the vehicle down, and then once we get down to even a lower altitude, we deploy what's called the base heat shield. And this is the heat shield that was facing into the wind during entry, that was keeping us cool during this time. Don't need that anymore, and so we deploy that. And what that does is that then reveals these 6 airbags, which are automatically deployed, inflated at this altitude, and then we just coast the rest of the way down until we touch down gently on Earth. There you can see the 3 main parachutes, numerous tests that we've done with those, and then looking at the loads and shock, if you will, at landing to make sure that the vehicle survives within limits. Once it's landed, recovery takes place. We have a recovery team which is pre-located at the appropriate landing site. They rush out to the vehicle, they open the door, and they assist the crew in getting out. Since the crew has been on space station for 6 months, they don't just jump up out of their seats and say, "Yippee, I'm here, I'm home, I'll walk from here." None of that goes on. Instead, the ground processing crew goes in and they carefully lift them out, and we have chairs which are similar to lawn chairs that are set down, lots of medical tests. We make sure that they're fine before we move them from that point. Similar to what's done with the Soyuz capsules that land in Russia today. So these are the 5 landing sites that I mentioned earlier. Starting at the top in red, that's a landing site in Dugway Proving Ground in Utah. Very large open area, nice smooth surface. When we land, we like to slide a little bit, and it's perfect for that. That big red diamond, that does not represent the entire landing zone. If it did, it'd be half a state big. Actually, our landing zone is much, much smaller, but that kind of represents some of our cross-range capability, whether we're coming up from the south or coming down from the north. Moving on to the lower right, we have 2 landing sites at White Sands Missile Range itself. One is at the northern end in orange there, and then the second one is at White Sands Space Harbor. White Sands Space Harbor is actually on the white sand itself, if any of you have been there. It was one of the backup landing sites for the Space Shuttle program, and in fact was actually used on STS-3. That was the only time the shuttle ever landed at White Sands. The great thing about White Sands is it's really smooth and it's really soft. It's almost like talcum powder, made out of gypsum. It's actually a national park. The bad news is it's really fine, and a little bit of that stuff in a high wind can get anywhere. So we have measures in place if we happen to land at White Sands Space Harbor to protect the crew and the cargo and the interior of the capsule in the event that we land on a windy day, like they did on STS-3. STS-3 was Columbia, and they had gypsum everywhere. So we know better, one of the many lessons learned from the Space Shuttle program. And then in blue, you'll see a location called Wilcox. It's actually Wilcox Playa, playa meaning dry lake bed. If any of you have driven on Interstate 10 through New Mexico, you probably drove right through the town of Wilcox. And about 10 miles or so south of that is where the playa is. And in fact, it's a great place to land as well. Big, smooth, dry lake bed. No trees, no bushes, no nothing. It's perfect for us. And then the last one is Edwards Air Force Base. Most of you are probably familiar with that. Edwards is a giant runway for Air Force test vehicles. It's a big dry lake bed as well. And in fact, it's right next to Armstrong facility, NASA facility. So there's both Air Force and NASA facilities there. Again, about two hours or so northeast of Los Angeles. I'll mention too, we actually did a survey of many other sites in the western side of the United States. In fact, I traveled to other sites that looked really good on the maps, and then you get there and there's these giant cactus bushes, which would not be kind to our airbags as we're setting down. Plus, we didn't think the state of Arizona would appreciate us coming in and trying to knock them over, so we said, we'll write that off. We'll try to stick to these big dry lake beds that can be found. So what happens if we're on orbit and we have a fire, or we have smoke, or we have toxic atmosphere, or a meteoroid strikes us and we have this big hole in the cabin? We've gone through great pains to make sure we can get out of orbit very quickly. Software will take care of matters, boom, 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 throw all these switches on its own, compute the deorbit burn solution, and get us out of orbit quickly. Well, chances are, if you have to get out of orbit quickly, you're not going to be lucky enough to be able to land at one of those 5 landing sites. And so we've chopped up the oceans and even lakes between the southern and the northern edges of the orbit that we can be in into 150 pieces. And each of these pieces are used by the onboard software to go find us a splashdown site to go to, and then relay that to the ground so we can go recover the crew and cargo. And so you'll see here we've got sites all over, Atlantic, Pacific, Indian Oceans. We even get into the Mediterranean Sea and the Red Sea and even the Great Lakes. Now, do we really want to land in the Great Lakes? No. Do we really want to land in the Red Sea or the Mediterranean Sea? Absolutely not. And so we've taken these 150 water zones and we've prioritized them from best to worst. The best zone is really located off the southern coast of California, off the Naval Air Station, San Diego area, and then they get prioritized from there. But if worst comes to worst and something were to happen, it's better for us to land in water than it is to land on land. And so chances are we'll never go to the water, and if we do, it's almost impossible that we would end up in one of these lakes. But just in case, we have that built into the contingency plan to make sure we save the crew. All right, so making a lot of progress at this point, and we're still working through some of the technical issues, but the vast majority of those are behind us at this point. We're really transitioning from design to production and doing considerable integrated testing, not just testing of the individual components, but the integrated spacecraft itself. The modifications to the launch site, those are nearing completion. A lot of training rehearsal sessions going on in Houston right now with the flight directors and their flight control teams. NASA doing a fantastic job getting those folks prepped and educated on what to do if things go wrong. So basically we're working forward to achieve certification of the spacecraft. What's the schedule look like? Well, flight tests are this year. As I mentioned, this summer for the pad abort test, third quarter for the orbital flight test, fourth quarter for the crewed flight test, and then we go into a NASA services phase of our contract. NASA has contracted Boeing for a total of 6 operational flights. You know, they might be 6 months apart, they might be 12 months apart. It's really up to NASA to dictate the schedule of all that. But we, Boeing, are getting paid for delivering on a taxi service a crew of 4 to the space station 6 times. Okay, here's a video. There's our capsule on top, kind of stick out from the rest of the body of the Atlas V. See the crew access tower off in the distance. We have liftoff. 2 strap-on solid boosters on either side give us the performance that we need to get into the proper suborbit. And then we're off and flying. Looks like the real thing, doesn't it? But no, this is not actual footage of our CST-100. That's yet to come. There's the solid rocket boosters being jettisoned from the main body. And there we go. We separate from the first stage. We're now riding on the second stage, Centaur. This is still during the first 12 minutes of flight. Then we cut off those engines, and then we separate from the launch vehicle. That's about 15 minutes after liftoff. And as I mentioned earlier, we're often doing rendezvous at this point. Even though we're still in a suborbit, our first burn will get us fully orbital as we go catch up with station. Those 4 engines you see on the back side are used to separate from the launch vehicle. Very heavy thrust to get away very quickly. The fuel, if not used for the ascent abort, is instead used for orbit and deorbit. There we are docking to the space station as viewed by a spacewalking astronaut who really shouldn't be outside during that time. And there we rotate into a deorbit burn attitude. You can see the pilot looking out the window. CM separates from the SM. CM has its own 12 thrusters that take over at this point during entry, descent. Separate from the drogue parachutes. Those are the main parachutes. The drogues actually tug on the mains to help them get released. Here's what we call a bucket handle, which deploys. That keeps the spacecraft at the desired attitude before we land on land. There's the base heat shield being released. These are the airbags being inflated. And then we're just along for the ride, wherever the wind takes us at this point. And then we have touchdown at one of our 5 landing sites. And that concludes my presentation.
Hi, I'm Dave Eicher, editor of Astronomy, and I'm here in beautiful sunny California at Celestron, the world's leading manufacturer of telescopes. Today we're going to get the lowdown on a secret, a new hot product that's unlike anything you've ever seen. So let's go inside and check it out. So Corey, Celestron has a really new, exciting, unique telescope. Tell me about the RASA 36.
Yes, the RASA 36, it's a 14-inch RASA. We have had the 11-inch RASA out there for a while now, and we have been secretly developing a RASA 36, a 14-inch version of it. It's still at f2.2, so you will get you very good speed, but with increased aperture.
And this is a really wide field, high-tech camera, astro imaging camera. You could capture incredible wide field views of the Milky Way, big vistas of comets, but there's a really special application that this telescope is perfect for. Talk a little bit about that.
We've been getting feedback from different people. One of them is from a lot of users in the SSA community. SSA stands for Space Situation Awareness. What that means is space junk detecting. More and more satellites are out in orbit, and inevitably they will hit one another, and they become space junk. A lot of them will stay up there for 25 years, and depending on in what orbit they're in, you can be up there forever. What SSA community does is they track these junk so that we can notify the satellite operators so they can maneuver to avoid them. We identify the need, we find a solution. We want to make astronomy fun, and at the same time, we also want to keep everybody safe.
For over a decade, the FirstScope has been one of our customers' favorite products. It's easy to use, affordable, and provides really impressive views for a scope of its size. When the time came to update the FirstScope, I teamed up with renowned lunar imager Robert Reeves to create a telescope that would inspire the next generation of amateur astronomers to explore the moon.
Hello, my name is Robert Reeves. For the past 59 years, the moon has been my passion. Why? Well, the moon is the closest world to Earth. The moon is in our sky almost every night. The moon is close enough that we can see amazing detail on the surface with even modest telescopes.
The Robert Reeves Signature Series FirstScope is more than just a telescope. It's your guide to the moon. The telescope tube is a map of the moon's most notable features so you can learn the moon's geography. This telescope walks you through the basics and unlocks the entire hobby of astronomy, making it fun, easy, and accessible for everyone.
So I invite you to get out under the stars and enjoy a voyage to the moon.